So hello everyone, thanks for joining our session. I'm Sagik Grimberg, Lightbit CTO. I have with me here Anil Vasudevan from Intel, and we're going to talk about NVMe over TCP and improving NVMe over TCP performance by enhancing software and hardware. So notices and disclaimers, which we're not going to read. And we're going to start with a short intro. The talk today is going to be primarily focused around Linux and the work that was done for Linux. The intro is not necessarily attributes to Linux, although it's heavily inspired by that. So NVMe over TCP is basically the standard transport binding that runs NVMe on top of standard TCP IP networks. That's all it is. It has a standard NVMe multi-queue interface that just happens to run on top of TCP sockets. It's the same NVMe command set, just encapsulated over what we call NVMe over TCP protocol data units, or PDUs. So if you look at the data at the diagram below, we basically have the NVMe architecture on top that defines the queue interface, command set, and whatnot. Below that, we have NVMe over Fabrics extensions that defines capsules, properties, and such. And below that, we have the transport specific features and the NVMe transport mapping that maps commands into messaging on top of the transport itself. And below that, we have TCP IP and the fabric layer, which is usually Ethernet. But NVMe over TCP transport binding are these two middle portions that that extends NVMe to run on top of TCP IP. So in NVMe over TCP, each NVMe queue pair, submission and completion queue pair, is mapped to a bidirectional TCP connection. And usually commands and data transfers are processed by a dedicated context. Could be a thread, could be a hardware context or whatnot. But if you look at the diagram, upper layers at the host side on the left has this logical concept of submission and completion queue, or however, it's not a memory map device. Sorry, not memory map buffers that talk to a device, but they talk to an IO context or an IO thread that is driven either from the host or from events from the network that says that it has new payload to sort of process. Now, the picture is sort of identical or similar in the controller side where it has this per queue NVMe TCP IO context or thread that processes both the network and talks to upper layer or the backend controllers, and it has the same logical submission completion queue abstraction. So this picture is pretty much on a per queue basis. You can sort of replicate that for different queues. So if we talk about queue mappings, each NVMe queue will normally be mapped to its own dedicated CPU cores, and you can have multiple CPU cores, each with its own NVMe queue associated with it. But that's not necessarily always the case. You can have more queues than CPU cores, you can have less queues, it's really depending on what you're trying to do and what you're setting up. But the important part is that there is no controller-wide serialization, right? So if we look at the picture here, we have an NVMe host and the bottom an NVMe controller. We have our admin queue, which is a submission completion queue pair, which is backed by its own TCP connection. And then for every individual core, you will have the same queuing interface or the same TCP connection with its own associated NVMe queue, which means that the NVMe host has this sort of parallel multi-channel interface to that controller. And that contributes a lot when talking about high performance and low latency. So that sort of attribute is inherited from NVMe semantics into NVMe over TCP as well. So with that, I'm going to hand it off to Anil to talk about ADQ and introduce you guys about that.
Thanks, Sagi. So what are application device queues, or ADQ for short? ADQs build on a long and existing history of advanced queuing and steering technologies by bringing a strong application focus into the picture. As shown on the graphic on the left, ADQ provides applications isolated and dedicated queue sets that create express lanes to traffic, express lanes for traffic to get to and from an application. With ADQ, you essentially reserve a queue set for an application. The identity of the queue is passed all the way up to the application. So which queue pair to select within a queue set is optimized such that you have a single producer consumer model between an application thread and the selected queue. Additionally, bandwidth control of egress traffic allows for traffic shaping per queue set, enabling better bandwidth sharing between applications if you so choose to enable that. The key thing is all of this is accomplished within the framework of the native OS networking stack. The table on the bottom right shows the full ADQ capability suite, ranging from the support provided by the NIC hardware through optimizations in the device driver and the kernel to get the maximum benefit from this technology. Specifically with respect to NVMe over TCP, there are many optimizations that have also gone in and have been upstreamed into the Linux kernel that Sagi is going to talk about first with the NVMe over TCP kernel host.
Okay, so let's take a step back for a second and talk about the possible latency contributors. If we want to have a low latency aspect, look at the I/O lifetime and let's look at what components can contribute into this latency. So first of all, serialization in general. In NVMe TCP, it's pretty lightweight. It's only on a per queue basis, which means it has its associated HCTX or hardware context and its associated socket, but it scales pretty well. So that's not a big issue. You can have context switching that can contribute to latency. We have two at a minimum contributed by the driver, and we'll talk about the work that's mostly driven from ADQ optimization that we do around that. We can have memory copy. Well, in NVMe TCP, we never copy data when we send it out to the network, outside from different corner cases. But when we get payload from the network, namely the RX side, we always copy the data into the user buffer. That's not a huge contributor, but sometimes in high load, that could be something that's meaningful. Interrupts, that's definitely impactful. The proliferation of interrupts, and you have a lot of interrupts that will definitely impact the latency and the overall throughput that you can get. Receive offloads through their various flavors or adaptive interrupt moderation can mitigate that a bit, but latency is less consistent, so it's a trade-off that you need to choose. Usually in the I would say out of the box experience, these receive offloads and interrupt moderations are on, but for specialized environments, these can definitely be tuned to achieve what you want. The socket overhead itself, it exists, but it's not huge. Mostly when you have a lot of small size payloads that you want to send to the network, that could be something that's observable, but that's not the determining factor for sure. There's affinitization. Obviously, we talked about affinity of queues, the CPU cores, and interrupts. So affinitization definitely can contribute to latency if not set up correctly. So we'll talk a bit about that. Cache pollution. Yeah, obviously we do memory copy on the RX side. So on different workload, it can have some cache pollution effects, not very excessive. And also we have head of line blocking that could be apparent in mixed workloads. So what happens is that NVMe over TCP is basically the messaging protocol on top of a TCP IP stream, which means that if a given queue is basically now in the process of sending a large write payload down to the controller. The messaging protocol sort of mandates that this transfer must complete before a subsequent small read that only has the command capsule in it is blocked behind it. Otherwise, you would violate the messaging interface on top of TCP, and you lose, the stream tracking. So in mixed workloads, this can definitely have an effect, and we'll talk a bit more about that as well. So we'll start by reviewing the lifetime of an IO, and we'll ignore a lot of the stuff that happens in the stack. But if we talk about the host side direct IO flow, it starts when the user issues a direct IO into a file or to a block device. Now we'll ignore all the VFS layer, the file system specific, the IO schedulers. Eventually, it goes down to the driver a callback where it's supposed to queue this IO down to the controller or adapter or down to the network. In NVMe TCP case, it's called the function, the callback is called NVMe TCP queue request. Now that prepares, it initializes the NVMe command, and it prepares a protocol data unit, a PDU, that's a buffer that it can actually send down to the controller, which would be able to parse it and understand it. But what it does, it places it on an internal queue. And we'll refer back to you on the picture that we have, that basically we have this IO context that's dedicated queue context, which is namely an IO thread that processes and serializes all the commands that travel on that queue. Now, what happens is that we queue the request, it prepares the PDU, and it places it on its own internal queue. Then it sort of wakes up this IO context that's called NVMe TCP IO work. It picks it up from its internal queue and it processes it. It basically sends it down to the network. It arrives to the controller. When it arrives to the controller, we're in step 4. The controller processes the IO. It completes it eventually, and it will send back either data or just or data plus the completion. That depends on the capabilities and the nature of the IO itself, and sends it back to the host. And then obviously at least one NIC generated interrupt will fire. Then we have NAPI is sort of triggered, pulling data from the NIC ring and pushes it up to the TCP IP stack for TCP IP processing. When data is ready for the socket owner, in this case our NVMe TCP driver, to read data from the individual sockets, then NVMe TCP data ready callback is triggered. And then we don't obviously process data back. We fire the same IO context that's handling both sends and receive. So we wake up this thread. That thread basically wakes up again. It checks if it has data to send or data to process. It finds the data. In this case, it has data to process. It reads data from the socket. If there's data to be copied into user buffer, it does that. And then it completes the IO, which eventually we're obviously ignoring all the other layers as well. Eventually gets back to the user. The user IO is completed. And then basically the application or user space application is free to go and do other stuff. Now we'll focus on these 3 parts along other things. We have an inherent 2 context switches. The first one is that when we get the queuing callback in NVMe TCP queue request, we basically prepare the PDU, but we fire off the IO context, the IO thread, to actually send it down to the network, which basically it's needed because of this serialization. We have the from the NIC generated interrupt up to NAPI, we have a soft IRQ that's trigger. NAPI always runs in soft IRQ context. And then when the data ready callback comes when data is ready to be read from the socket, we basically fire the same IO context back again, which is a second context switch, or the second context switch. Now, these obviously contribute to latency and the overall throughput, on high load. And I guess that optimizations that were done, driven mostly by ADQ, will tackle these three. So first, I want to revisit back around the head of line blocking and the mixed workload problem that we alluded to before. So we talked about the fact that basically the messaging interface on top of TCP/IP mandates that if you start a request that you're going to transfer data, you can have other, small reads bypassing long and large writes. So to our help, the block layer now allows multiple queue maps or queue sets that will basically host different types of IOs. So we have three different maps that are available to us. First of all, the default, which is the normal set of hardware queues or the hardware contexts. Basically, all the IOs that won't fall in the two other queue maps will hit this normal queue map. Which in our case for multiple queue maps will host mostly writes or requests that requires transfers, large transfers or even small, from the host down to the controller. The second queue set, or queue map, we call read. Basically, every read IO will be directed into this queue map or queue set, which maps into a different NVMe queue or a set of NVMe queues and a set of its own TCP connections, which means now that you don't have this head of line blocking, because now reads and writes are basically sent on different NVMe queues, which means that they are sent on different TCP IP connections. The third queue map is what we call poll, and these are dedicated queues that are dedicated for polling applications, or basically all the IOs that has the high priority flag marked on that IO will be directed into this queue map, if it's available, of course. Now, the elimination, as I said, of head of line blocking of small reads versus large or competing large writes is that basically reads and writes has their own dedicated queues, which means that they never conflict. So what we did is that we basically added support to allocate more queues than CPU cores, and basically plugging these options or these extra set of queue maps into the queue map infrastructure in the block layer. Now, the way we tested and show the value is a simple test that has a 16 thread reader, or 16 applications that are reading synchronously 4K, which means that every reader is doing a single synchronous 4K read. And then we have one outbound writer that's issuing large 1 meg writes at a queue depth of 32, and it sort of bounces around between CPUs and uses different queues to transport these 1 meg write requests. So in the baseline, we see that you get around 80K IOPS for reads on these 16 readers. Average latency is almost 396 microseconds, average latency for a read request, and the 4 nines gets pretty bad when it gets all the way up to 14 milliseconds in this extreme case. Now, once we added support for these multiple queue maps and have dedicated read queues, we see that write IOPS has more than doubled with 171K IOPS for these 16 readers. Average latency correspondingly reduced by more than half, now with 181.5 microseconds. And the tail produced in almost an order of magnitude improvement on the 4 nines tail latency. So that was a definitely an improvement and a recommended case to use when working in um, a latency sensitive workload environment. Next, some affinity optimizations. We said that we alluded to that when we talked about different NVMe queues, and then we have basically for every queue we have a thread or an I/O context that's responsible for issuing all these I/Os and serializing that, which means that we have affinity between an NVMe queue, this I/O thread context affinity, and the NIC interrupt affinity as well. So as we said that Linux basically now grew the capability to split different IO types to different queue maps, you know, the normal, the default, the read, and the polling. Um, so what we did is we optimized the IO CPU. That's the marker that says where the IO context of that specific queue will run on in the case of a multi-CPU environment, which is most of the cases. Now, in case that we have different queue maps, this what happened in the baseline that the accounting for assigning these IO CPUs were combined for all the queue maps as one, which doesn't feel really the general use case where you have basically multiple queue maps and you want them to be sort of aligned into how you want to affinitize them. So we basically the alignment calculation or accounting now took into a symmetric approach where each queue map will have its own accounting that will fit pretty nicely with the the CPU cores and the application affinity and the NIC interrupt affinity as well. Of course, this is most important in read and poll queue maps where IOs that are more I would say latency sensitive. This becomes much more important. And we did a micro benchmark to test the improvement, and we have two graphs here. One, the blue is the baseline, and the red is patched, which means that it has this optimizations in place. First one is QDAP1 latency measurement, just omitting media latency, just the transport itself. So QDAP1, basically we have the IO completed or the network or the transport overhead of 30 microseconds in the baseline. And that we got a 10% improvement to 27 microseconds just by affinitizing better. But also in high QDAP, which have, again, a single threaded applications issuing at 4K read IOs at a QDAP of 32, we dramatically improved them from 179 K IOPS as a limit up to 231 K IOPS for that same limit. Now, of course, don't take these numbers as absolute numbers because that really depends on the platform and the configuration. But relatively, we could see an improvement for sure. Next, we'll tackle these. The attempt is to tackle the context switching that is inherent to the driver and the presence of this IO context. So first, the optimization was in the TX path. We mentioned that when the request is queued from upper layer down to the driver, we initialize the command, prepare PDU, and then we defer to a different IO context. That IO context will probably, in the common case, will run on the same CPU and will just incur just a context switch between the application thread that issued the IO into this NVMe TCP thread that will send it down to the network. So we want to eliminate this context switch and actually send the request down to the network from directly from the queuing callback and basically just omit this IO context. That required, because network sends in Linux, they might sleep depending on, congestion or, other phenomena. So we basically need to convert the locking scheme in the block layer to a sleepable context or an SRCU. And now we basically have two contexts that are both can potentially process the same socket on the TX side. So we need to serialize between both of them. So we introduce a mutex to control, to serialize, make sure that we don't get out of sync because two concurrent threads or contexts are processing the same socket. So we introduce a mutex to serialize between them, but to sort of relieve the fact of contention around this locking element, we only take this mutex if the queue is empty. I mean, if we already grew a queue that we have ready request to be sent down to the network, we don't acquire the mutex. We just queue that command and let the IO context process that as well. And if the running CPU matches the IO context affinity CPU, which means that if we're competing, we're only competing within the same CPU core or hyperthread. That basically guarantees us that we won't have different CPU cores, possibly on different NOMU sockets, competing on the same send, which is, again, bad for latency. The second improvement was setting a socket priority, which is the interface for us to leverage some of the ADQ technology, steers egress traffic to the preferred NIC queue set. Anil is going to talk about that further soon. But these combinations basically contributes to latency reduction, eliminating a context switch and also leveraging ADQ. On the RX path, obviously we had again a context switch from NAPI telling us that we have data ready to be read from the socket. We context switch into the same NVMe TCP IO context that will read data from that socket and copy it to the user buffer and or process completions, depending on what's coming from the socket. So for workloads that are polling driven, and there are some more latency hungry or IO hungry latency sensitive application that will definitely rather poll, Linux grew sort of a support for that. Application can submit a high priority flag for a request that it's interested to sort of indicate to the stack and all the way down to the device that it's interested in completing it fast. And it also has an interface to actually poll and not be sort of woken up when the IO is ready, but to actually sort of poll for this completion. That option is available through IO Uring. That's a new interface we won't get into, but that was the tool that, or the interface that we use to measure the performance and the latency reductions. What we did in NVMe TCP is basically we plugged into this polling interface in the kernel and specifically in the block layer by adding a callback that's called NVMe TCP poll that plugs into the polling infrastructure in the kernel and the block layer. So as I said, we added more queues, dedicated queues for polling. You can signal that through the connect options. When you connect to an NVMe TCP control target or a controller, you can specify that you want one or more poll queues. And then when we're actually being called for the poll function, we trigger SK busy loop, which means that we're going to actually poll from the NIC RX ring specifically. So once we do that, we're actually polling from the user, goes down to the driver. That driver will basically pull that RX ring NIC, and then we'll basically get the completion by polling instead of waiting for an interrupt. Now, obviously, that helps with RX moderation. If the NIC can hold off interrupts more aggressively, that works actually very well. And the third part is that if we added infrastructure to detect that we're basically polling, and then when the data ready callback comes from the network stack up to the driver, we sort of look for a flag if we're in the middle of a poll. if the application is just polling us. And if the application is just polling for a completion, we don't really context switch into the NVMe TCP IO thread that will, as I said, read data from the socket. We'll let the polling hook to basically process this data. As I said, this works fairly well. So we measured combined the TX and RX optimizations on the same micro benchmark. And we saw also similar reductions. So for QDAP1 latency, instead of the 27 microseconds, now we have another 10% improvement. So we have 24 microseconds additional to the media latency. And in a high QDAP for that, single thread, we have latency IOPS improvement or throughput improvement from 230K 4K read IOPS up to 247 4K read IOPS. So this is by basically eliminating these two context switches. One is the TX path when we send a request down to the network, and one is when we get a completion and we allow the application to actually pull for it, and we don't incur this extra context switch on the RX path. All right, and with that, I'm gonna give it back to Anil to talk about some of the NVMe TCP target optimizations that we did.
Yeah, so let's look at some of the target optimizations. So let's discuss some of them. So the first one that's called out here is to assign IO threads based on SO incoming CPU. This technique here helps to reduce context switches because the associated IO thread would be on the same core on which the inbound request came. But depending on the situation, this may cause an uneven system balance. As an example, if the distribution of connections amongst queues is skewed, then you may see a little imbalance. Because on a NIC, typically the inbound connections are load balanced using a hashing scheme like RSS. The second one is about grouping. Grouping multiple connections to a single IO context. By grouping, what you're able to do is, because you're able to group multiple connections, which means essentially multiple NVMe queues to a single NIC hardware queue, it enables better efficiency with each context processing on the NIC hardware queue. In terms of polling friendly heuristics, because one of the main things here is for instance, with technologies like ADQ, you're trying to improve the predictability and you're trying to get far fewer context switches than you would normally see. So polling friendly heuristics are important. And so we introduced a polling budget based on poll groups, which ultimately in the polling friendly heuristic reduces context switching, and the interrupts are fewer because of that. But at the same time, we maintain fairness per connection. The other optimization of the target is sockets are open for the target. We set the socket priority. The priority enables traffic steering to a preferred NIC queue set, and we'll get into a little more details on that as we go through the following slides, which talk about ADQ specific improvements. So what are the ADQ improvements that you would get in general with NVMe over TCP? So one of the key aspects of ADQ is to isolate traffic into a dedicated queue set. So in the case of NVMe, we direct NVMe traffic to its dedicated queue set, which on the inbound side, the dedicated queue sets are configured using the traffic TC mechanism, traffic class that is there in Linux. So we use the TC prio traffic filtering to filter traffic to a queue set. And I'm sorry, we use TC prio to dedicate queues and a queue set, and then we use TC flower to perform traffic filtering for that queue set. And then we have to decide how we pick queues within a given queue set. And for that, we use RSS or flow director. On the outbound, like we discussed earlier, we set the socket priority, and the socket priority allows us to steer traffic to the corresponding application queue set. And that is done through extensions in XPS that allows the choice of the specific TX queue within a queue set. So basically what happens here is when you create a dedicated queue set through mqprio, you also set a priority, and that priority is honored on the egress path. When a socket with the priority comes through, you can then pair the queue sets based on that. The value proposition from this is that since you have dedicated and isolated queues, there's no noisy traffic from neighboring workloads. So it is a very key thing with ADQ in that if you're able to guarantee that traffic for NVMe over TCP is the only traffic that is flowing through these queues, that allows you to, that provides you an opportunity to customize network parameters specifically for NVMe over TCP. Continuing with the ADQ improvements, one of the key improvements that ADQ provides is the ability to minimize context switches. Minimizing context switches is super important. And the various ways by which the minimization of the context switch is done, but is first busy polling on a dedicated queue set. So when you busy poll on a dedicated queue set, you have the ability to drain your network completions in the context of the application, in this case, the NVMe over TCP. You can also process completions directly in application context because you're polling the queues, the poll goes all the way down to the NIC queues, you're pulling the data from the NIC queues, it comes back all the way. And so the requests and the responses can be serviced in the context of the same application without undergoing context switches. So that's the second bullet where we handle request response also in application context. And what that does is that it keeps the application thread active. And there are no redundant context switches as a result. Grouping multiple NVMe TCP queues to a single hardware queue allows very effective sharing of NIC queues. For example, polling can then handle requests from multiple NVMe TCP queues to improve throughput on a core without redundant context switches. So by doing this, one of the key things in ADQ is that you try to really provide improved predictability. And while focusing on predictability, you also get, the side benefits of improved throughput and latency. The value prop here in terms of these improvements is you also, in addition, because of the grouping, you also have the ability to reduce CPU utilization as a result, because you're really processing traffic in the most efficient way possible on a given core without any context switches and with busy polling so that you get the maximum throughput out of a core. So let's take a quick look at this data that's being shown here, what you can see is that for Q depth equals 1, and depending on how aggressive your adaptive intermoderation is, the latencies on this platform are, just a shade under 20 microseconds for block requests to a RAM disk. And while you compare it with ADQ, that, for a similar, for the same test can get you roughly a couple of microseconds faster. So it's at around 17.7 microseconds. For Q depth 32 with Optane, with ADQ enabled on the initiator and the target, you're able to get about 341K IOPS compared to the baseline, which has some interrupt tuning to get it up to the 245 or 250K mark.
Okay.
So with
that is basically the kernel-based implementation. This is just by turning on ADQ versus not.
That's correct. So with that, Sagi is going to take you through a description of the LightOS target and some performance measurements against that target with a kernel ADQ enabled host.
Thank you. So we're going to give an example of LightOS, which uses NVMe TCP as an interface, but provides a number of aspects, more being as providing simplicity, availability, reliability, scalability, and also low latency, especially with ADQ enabled. So if we look at the configuration of a deployment of LightOS system, we have on the left these application servers. These are Linux boxes that supports NVMe, NVMe over Fabrics, and NVMe over TCP. They could be orchestrated together using something like Kubernetes or OpenStack, which is supported by our platform and integrated. And it hosts all the applications that are that need storage, basically. In the middle, we have our standard TCP IP fabric. And on the right-hand side, we have our LightOS cluster, which basically is a software-defined storage, which means that these servers are off-the-shelf x86 servers with an Ethernet NIC and a set of NVMe SSDs. We mount our software on top that provides, and we cluster these servers together. We have an NVMe over TCP cluster or a storage cluster that provides capacity through NVMe over TCP. And we have an optional acceleration card, which is a PCI add-in device that offloads some of our data services, which is optional. Both are supported both with and without acceleration. So the clustering nature of the system is multi-rack and scale out in the sense of how it sort of topology aware. So if we look at these three different fault domains, we can basically take a number of nodes from each fault domains and cluster them together in one logical cluster and feed the cluster information awareness about our fault domains, which means that both automatic failover can happen between racks or fault domains, and the volume placement and volume replication strategy is also topology aware. That means that blast radius or complete rack failures or fault domain failure are definable now and can be highly available across that. The high availability aspect that we provide is basically on each individual node we'll have RAID protection or a flexible RAID ratio coding scheme that can protect us against individual SSD failure, given that our nodes can be dense. We don't want an individual SSD failure to result in a cluster operations. But every volume or NVMe namespaces or NVMe namespace has different protection policies, which means that it can be either non-replicated volume, which means that it will sit on one node or one server in the cluster, or it can be two-way or three-way synchronous replicated. The way that we sort of reflect that capability or that clustering scheme up to the host is using NVMe multipathing or ANA asymmetric namespace access, where every node basically presents an access state with respect to an individual NVMe namespace that could be an optimized or a non-optimized. And all the replication happens within the cluster. It's not driven by the client or the host. That allows us to both do rebuilds, balancing activities without the client being aware. All the awareness gets through NVMe in-band events that notify ANA state changes, which means that the host will now choose different IO schemes to access its capacity. Also, network failover with link bonding or teaming, that's also obviously supported and used in the field. And all the auxiliary services like an API service or the NVMe discovery service are all highly available as well. In addition, you get data services, of course, like logical volumes, thin provisioning, inline compression, online capacity expansion with SSD hot plug or adding more nodes or clusters, with online volume resize and ratio coding, obviously. And we have some flash management capabilities, and this is a lot of the value proposition is that we are able to improve the endurance of these drives with our, um, uh, um, I would say, backend and FTL, which means that we inherently support QLC, and that provides both low latency and endurance improvements. Now, what we did is that we used our cluster to test an ADQ enabled host. So we have here in the drawing a host that's connected to its top of rack switch. That host has basically the ADQ enabled adapter, the E810, running a very mid-range Xeon CPU Gold. And Linux kernel 5.7.0 with all the improvements that are incorporated in that. That is connected to a spine switch, also through a 100 gig interface, and that connects down to a leaf switch that's connecting a LightOS clusters or a 3-node cluster that all running LightOS, which means that the capacity is virtualized, and now the host can access all 3 of them, capacity from all 3 of them. Now, that's the minimal size of the cluster. In Lightbits, obviously, we could have had more hosts connecting to it to get more throughput. So in a single thread, what we see basically, we took the same single thread workload from that host, and we saw the improvements from ADQ versus non-ADQ, both on the mean latency on the left-hand side, which can result up to 50% improvement on the average latency depending on the queue depth. We have basically a variance in queue depth between 1 and 32 for that single thread. And on the tail 4 nines latency, we can see an improvement of up to 30% depending on the queue depth as well. If you look at the right-hand side, we have up to 70% improvement of a single thread 32 queue depth load. That means that we have higher IOPS and lower latency for that thread that's now leveraging ADQ. Now, on the multi-thread case, we basically took now, instead of a single thread, we have 32 threads that are all issuing IO to the cluster. And we can see that by enabling ADQ, we can improve by 30% average latency and 4 nines latency compared to not using ADQ. And similar improvements in IOPS. So we see that basically without having ADQ, we're pretty much capped at 2.2 million IOPS for 4K reads. And with ADQ, we're able to get up to 2.8 million IOPS. We actually need slightly less than that because obviously the tail latency is sort of jamming because of the network bottleneck. So with that, you can ask questions, take a moment to rate the session, and thank you very much.
Thank you.